Hello AP Calculus, I've got a new video for you. 5.2 is all about determining relative extrema. Okay, so the first derivative test is the name of the game for this first video. But I wanted to unpack what relative extrema, what that phrase means. Extreme values just mean the highest peaks and the lowest valleys. So when we're talking about relative extrema, we're talking about max and min values. Not the absolute max or min, but we're just talking about like these types of situations for max and these types of situations for mins. Right? So if this were a curve, this would be a max value and this would be a min value. And this would be a min value. And that would be a max value. But we would call them relative max or min values because they're not the absolute highest points and lowest points. They're just, relatively speaking, in a little window there. It's like, hey, these are the high points and these are the low points. Make sense? All right. So the question is, how can we use derivatives to determine what these little points are? And if you're already thinking about intervals of increasing and decreasing, then you're on the right track. Because look at this. It's increasing, and now it's decreasing. It's increasing, and now it's decreasing. So we're going to be using derivatives to figure out what the max and min values are. So my first example in unpacking this. F of x is equal to the function 2x to the third power minus x plus 7. Sorry, minus 6x plus 7. Now, just from our pre-calculus knowledge and a little bit of what I talked about in the last couple videos, you should have a pretty good idea of what this curve looks like. The leading power is odd. The leading coefficient is positive. And there's another x value in there. That means that we should have this n-like behavior. I use the letter n because it kind of looks like an n right there, yeah? So we should be expecting probably at least one max and one min value based on what you're seeing right here. So what do we do first? Well, the first derivative test requires us, surprise, surprise, take the derivative of it. And this will be relatively simple. It's going to be 6x squared minus 6 plus 0. We're actually going to try to set up our intervals of increasing and decreasing like we did in the previous section. Like I was saying, if we can figure out who is increasing and who is decreasing, we could probably piece together where that max or min value would be. So we need to find our critical numbers. We can divide everybody by 6 here. That'd be 0 is equal to x squared minus 1. And this is just going to give us x equals plus or minus 1. These are our critical numbers, more affectionately known as crumbers, or we could even go crumbs, right? So negative infinity to negative 1, we're going to bracket it for intervals of increasing and decreasing. Bracket, bracket, and then just test a point like normal. Are we increasing or decreasing over this interval? Are we increasing or decreasing over this interval? Same for the last one. So we should probably plug into the unaltered version of the derivative, which is this right here. I don't think it really matters, though, if we divide it out by 6. Whatever the case may be. Plugging in a negative 2 here gives us positive 4 times 6 minus 6. It's going to be positive. That means that we are increasing over the interval negative infinity to negative 1, which seems to be confirmed by our rough sketch drawing. So it's increasing. Plug in 0, you get 0 squared times 6, which is 0 minus 6, negative. So then we go to decreasing. So at this very point, negative 1, we go from increasing to decreasing. Test 2. 2 squared is 4. 4 times 6 is 24. Minus 6 is positive 18. That one's increasing. So it continues to go down, continues to go down, continues to go down, but then it has to come back up again. At 1. So think about this. If my derivative, okay, at a specific point here goes from greater than 0 to less than 0, we will always have a relative max at the point at which it changed. Okay? So this situation right here creates a relative max. At x equals -1. And then here, when f prime at a specific value, okay, the specific value we're talking about is 1, all right? When f prime goes from less than 0 to greater than 0, it's always going to have this decreasing to increasing change. By the way, it's got to be continuous because it's differentiable. Back in the day, we talked about how a differentiable function always implies that it has to be continuous. So going from less than 0, decreasing, to greater than 0, increasing, always creates a relative min. In this case, at x equals +1. In essence, this is the first derivative test. We're assuming that our function is differentiable and continuous, and yeah, there's the first derivative test. So we've confirmed right there that there is a relative maximum at -1, comma something. And we can actually determine the y value very easily by plugging into f of x. So, you know what? Let's do that right now. -1 cubed is -1 times 2, -2. -1 times -6 is +6. -2 plus 6 is 4. 4 plus 7, 11. That's literally the point where our maximum value exists. Our relative max is -1, comma 11. If we did that with the min, we would get -4 plus 7 would be +3. Okay? Now the instructions on your homework, yeah, we need to actually find that coordinate, so make sure that you guys find the two y values. Okay? Let's unpack this with one more example. Let's throw some trig in there. I'm going to do number 25. Number 25 on the handout that you guys are seeing in Google Classroom. I'll write it up on the board here. Nothing too fancy, sine squared of x, where 0 is less than x, which is less than 2 pi. So they're basically saying, hey, let's restrict this between 0 and 2 pi. Let's not include the actual boundaries. Now, to put some perspective on this graphically for what this looks like, they're basically saying, take a sine function, okay? And a sine function starts at 0, moves to its peak at pi over 2, then goes to a valley, peak, valley, kind of like this. And what it does, though, is when you square it, it makes everything that was negative now positive. And it's not going to be just a straight reflection of it because you're squaring all the values. So if one of the values on the bottom was a half, squaring that creates a fourth, so it's not as high as what it was before. But bottom line is, sine squared looks something like this. Instead of going below, it kind of repeats a similar pattern like this. So sine squared's kind of funky looking, but as you can see, there's going to be lots of peaks and valleys to work with. So let's get to it. So step 1, find f prime. So you bring the 2 down, repeat sine of x. It's now to the 1 power, but you still have to take the derivative of the inside. Think of sine squared like this. Chain rule says bring the 2 down, repeat the inside, take it to the 1 power, then multiply by the derivative of the inside, which is cosine of x. Step 2, compute the crumbers, the critical numbers. Get those critters. Set f prime of x equal to 0. So 0 is equal to 2 sine of x cosine of x. Now there's a couple approaches I could take here. This is actually a double angle formula, but I could just as easily say 2 sine of x equals 0 or cosine of x equals 0. That's called the zero product property, where if 2 entities are multiplied together and you get 0, either one has to be 0 or the other has to be 0. So divide that 2 out. Where does sine of x equal 0? Where does cosine of x equal 0? Well, if you think about your unit circle, sine is 0 where the y values are 0. So 0 and pi. And really 2 pi, 3 pi, 4 pi. But again, we're restricted between 0 and 2 pi. Cosine equals 0 where the x values are 0. So at pi over 2 and 3 pi over 2. So this gives us a critical number of pi, pi over 2, and 3 pi over 2. 0 is already an endpoint, so that's going to be included there. So, step 1, find f prime. Step 2, find those critical numbers. Step 3, set up our intervals of increasing and decreasing, test them out. So set up and test intervals of increasing and decreasing. So here, let's get some more room. So pi over 2, then to pi, and then 3 pi over 2. So part 3. We got to start at 0 because it doesn't go to negative infinity. Pi over 2 is the first stopping point. I'm going to put a parenthesis here because of that. But because this was a critical number through zeros, that's fine. Then pi over 2, make a pit stop at pi. Then make a pit stop at 3 pi over 2. And then go 3 pi over 2 to 2 pi. Test a point. I'm just going to pick all the pi over 4 values that live between. Now, you're plugging into f prime. Okay? So f prime was this right here. I guess maybe keep in mind that 2 sine of x cosine of x is equal to the sine of 2x. That double angle formula is actually pretty helpful here, because what you do is, if all you're doing is taking the sine of double pi over 4, well, double pi over 4 gives us a pi over 2 value. And that's a lot easier to think about. The sine of pi over 2 is going to be positive 1. The sine of double 3 pi over 4 is the sine of 3 pi over 2. That's going to be negative 1. and then the cycle just repeats itself, because once you go to 5 pi over 4, that's double 5 pi over 4 is 5 pi over 2, yeah? So now we're back to plus 7 pi over 4 becomes 7 pi over 2. We're back to negative. So you're going from increasing to decreasing, decreasing to increasing, increasing to decreasing. So you've got relative maximum values at pi over 2 and at 3 pi over 2. You've got a relative min value when you go from derivatives being negative, decreasing, to derivatives being positive, decreasing. And if we need to find the actual coordinates for those, which I'm asking you to do, you just plug pi over 2 back into the original. Plug 3 pi over 2 back into the original. Plug pi back into the original. Which, when you do that, sine of pi over 2 is 1. 1 squared is 1. So there's the first relative max value. 3 pi over 2, it gives you the exact same thing. When you plug in sine of 3 pi over 2, that gives you negative 1. Square negative 1. You got 1. So these are your points at which you hit your max peak over the course of 0 to 2 pi. You hit your minimum valley when you plug in pi. The sine of pi is 0. 0 squared is still 0. So these are your max. This is your min. All right, now does that kind of like meet our original test there? Because what we had was, we had a graph that looked like this. From 0 to pi, down to 0, again, it had to move right back up at 0, and then moves down again. So this is pi. Seems to be a min value. These are the halfway points between them. It works. All right, guys, 18 minutes seems like a good stopping place for talking about the first derivative test. I will now go over the second derivative test in a new video. Thanks for watching.